And I'm not sure what I can do about that. I've got a couple ideas and I've got a couple emails into people to see if I can fix that. But that might be our best bet, is for me to basically do section by section chunking of, 10, 12, 14-minute videos. And then we can spend most of this time, I hope, problem solving. I wrote that down, Daniel, OBS Studio. Look, here's the honest truth. There are so many supposed choices of things we can use that it's almost overwhelming. And each and every one of these choices has some limitation that hangs me up. And so I'm getting to the point where I'm just going to pick two things and I'm going to stick with them. I'll have my technology consultant, better known as my oldest child, check it out for me. But for now, at least for this week, we're going with Zoom unrecorded because they're just not loading, and a couple of Canvas Studio videos, and I'm going to see if I can get Studio to behave itself better. Canvas Studio is also the one that the VCCS is really, really, really encouraging us to use. I'm going to see if I can make it work. But I will get my oldest to go check out OBS because I am not familiar with that at all. All right, shall we roll? Do a little polyprotic acid stuff?
Let's do this.
You guys fine with that? Oh, look, there's someone with a microphone. It is also, by the way, guys, if you haven't figured it out, unbelievably bizarre to sit here and talk to a machine and not have you guys talk back. It breaks my heart. That's why I teach, is so you guys can talk back. But we'll do the best we can, okay?
Mm-hmm.
Fair enough? So, yeah, talk back. I'm all good for it.
Okay.
Let's move on. Let me see what I can do here. Oh, as I remember how to do this. Come on, machine. Because now I've been on Studio, and now I've got things. There we go. All right, we're going to do the polyprotics. And I will get a Studio video up on this as well. All right. But in the meantime, polyprotic, just more than one ionizable hydrogen, guys. All right. So here we've got, the sulfuric acid, diprotic, phosphoric acid, triprotic, a lot of the organic acids, malonic, citric. Citric acid is, I believe, a triprotic acid. And the thing is those are all H pluses that can come off, but they come off one at a time. The way we treat them is to have them ionize in steps. And that means that each step has its own Ka. All right. There are not, this doesn't make any sense, there are not any bases that do a similar thing. So we're just worried about the polyprotic acids. Oh, there we go. Now I'm back on. There we go. But now I'm going to have to erase that. It's going to be one of those days, guys. It just is. Anyway, so phosphoric is a classic. All right, phosphoric. Now the machine is talking back. Thank you, Daniel. You're going to be the one who keeps me sane, Yeah, there's the undo. I've got it now. And again, appreciate, guys. I've got so many different sets of instructions for how to manage this stupid annotation that, yeah, I keep confusing them. But yes, there is an undo. And I see it now. Thank you, Daniel. You're going to be the one who keeps me sane, Daniel. I think so. But anyway, phosphoric is the classic. Polyprotic weak acid. All three of those protons, all three of those ionizable, H pluses. See, now you're going to make me laugh while I'm trying to lecture, Daniel. All three of these come off sequentially. All three are weak, and boy, do they get weak. All right. So you see the first step. You just take the phosphoric, 3 ionizable protons. First one comes off. We make, so we got our acid, we got our base. So that means this is now the conjugate base. That is a dihydrogen phosphate anion. And there's our hydronium ion. And you can see that the Ka is pretty small. Yep, get rid of the H2, but we have, Michael, but we haven't put it in the expression yet. Right now, we're just writing the reaction. But yeah, you can, if you want to write the abbreviated form of these equations and get rid of the water and just do H3O or H3PO4 makes, or is in equilibrium with H2PO4 minus plus H plus. That's fine. Lots of people do it. But you can see it's pretty small. Ka. All right. Boy, we'd like that one to be, we'd like that initial concentration to be fairly concentrated so we can still use the 400 rule or the 400 guideline so that we don't have to use the quadratic. But once you've got the dihydrogen phosphate anion, you carry on, I hope. Oh, it's going to be a but. Hang on. I got to get back to the mouse. There it is. And again, the dihydrogen phosphate will ionize to a very small extent in water to make the hydrogen phosphate anion and more hydronium. And notice that the Ka went down by a power of 10 to the 5th. It happens again until we've done gotten rid of all the ionizable protons on there, and you can see how tiny that third Ka is. And that is a great and wonderful thing because it simplifies our lives when we get to setting up all these ice tables. All right, a few more words, blah, 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 blah.
Professor?
Yes.
So the K changes by a constant factor?
Nope.
Oh, so it's...
The
okay.
K changes by whatever nature decides it changes by.
Okay.
Okay, but usually the jump is significant. All right.
Yeah.
And the reason down there, you can see reason number 2, it is more difficult to remove an H plus from something that is already negatively charged. So the difference in these sequential Kas is usually large, 10 to the 4th, 10 to the 5th, 10 to the 6th.
Because we're removing H's?
Because we're all continuing to remove H pluses from something that is already a minus.
Okay.
Okay, makes sense?
Yeah, okay.
Okay, cool. On we go. Let's go do some math. Except for this thing keeps there. Whoops, sorry. Yeah, it's just going to be a but. Sorry. And my apologies to anybody who doesn't appreciate my language either. Oh, but now my see, all these wonderful things that are not behaving themselves with respect to, yeah, the undo just didn't work, Daniel. But I'll get it figured out. Here's a bunch of them. All right, we can sit here and look, and you can see, look at that, the ascorbic acid, the jump between the first Ka and the second Ka, what, 10 to the minus 7th? You can see the 3 for citric acid. The jump between the first two is not that great. It's only, about a order of 10 to the 1st. You can see that some of them start super, super small already. Hydrosulfuric acid is not very acidic at all, guys. That's the first Ka. Whereas you know that sulfuric acid is a strong acid. Oh, malic, oxalic, and there's phosphoric at the end. So anyway, we move along with those. And we get to something like this. Using, let's do the math. Using the ionization constant, so the Ka is for hydrosulfuric acid, which we know is not very acidic in the first place. We're going to calculate the pH And then notice that we're going to calculate the sulfide ion concentration. So we're going to have to do this thing twice. And this is analogous to one of the problems I put on problem solving assignment number 7. All right. That one is, whichever one that is, it's diprotic acid. And we're going to do it twice. So follow along. All right. Yeah, it's ice tables from now on for several minutes. All right. The good news is once we get to buffers, we get to dump the ice tables for a few minutes, which is great. But for now, yes. So some of these ice tables, because you guys are probably getting bored with ice tables about now, some of them I'm going to go screaming through. And I'm going to tell you, if you're not catching it, that you need to go back and just kind of stare at the PowerPoint and do it, because otherwise everybody's going to get, this is tedious. We'd be having much more fun in the classroom. But anyway, we're just going to start this thing. And it's the same drill, ladies and gentlemen. We're going to start with the unionized or undissociated initial concentration of acid, 0.100 molar, 3 sig figs. We have none of the dissociation products, and we carry on, and we lose X molar, we gain X molar, we gain X molar, and you're saying this is boring, and that's great. I need it to be boring at this point. I want it to be boring at this point. I want this to be trivial for you. All right. And we're going to sit there and we're going to solve for X. We're going to do our thing. What is our first? Now realize this is the first dissociation. So you're going to use the first Ka. So 8.9 times 10 to the minus 8th. Boy, we know the 400 rule is in effect, right? It's not boring. It's tedious. Oh, we can absolutely use the hack, Daniel. Absolutely, absolutely. Again, take a look at that problem solving assignment. There's one of them you can't use the hack, and it's really obvious. There's something on there with a Ka of 0.42. So I'm not even going to waste our time putting that minus X in there. This is what we're looking at. All right, and we're going to solve for X, and everybody's got their calculator, and we're going to do 8.9 times 10 to the minus 9th times 0.1, and we're going to take the square root of that, and I'm going to get X equals, somebody double check me, I know it's on the next slide. I just got 2.98 times 10 to the minus 5th. Somebody double check me. And I got to watch it, let's see, sig figs. Nope, our Ka is 2 sig figs. So actually it should be, what, 3 times 10 to the minus 3.0? Times 10 to the minus 5th. Somebody double check me. I'm going to go to the slide anyway. I'm going to go to the next slide anyway. But, so we've got X. And X is that hydronium ion concentration and the hydrogen sulfide ion concentration. All right. And I am, because I think what's going to happen here, I'm going to clear my drawings as we go to the next slide, because again, I got to figure out this machine. Nope, I missed it. Oh, we already did that one. We've got it. But here's the deal. It's only the first time. Ooh, hey, somebody double check my numbers. Did anybody get that one?
Yep, I got that one, but I was just double checking.
Yeah, no, something's up. Because I did this one yesterday. Let me go back. Let me pull up the other slide. Where am I? Let's try that again. What did we end up with? 8.9 times 10 to the minus 8th?
Yep.
Wait, but that's the Ka1.
That's the Ka1.
And then we multiply it by 0.1.
And then we multiply by 0.1, which we got.
And
Oh,
then we
that's
square root.
8.9. That's 10 to the minus 8th times 0.1. Square root. Okay, there. No, yeah, no, I screwed up
Oh,
in those annotations. If I continue on in that annotation, I screwed up. This is correct. Double check me.
Yeah, I double checked is correct.
That's correct. Okay. So I dorked it on the previous slide. But now, so that was X for the first ionization. Well, now we have to go on with the second ionization. Look at the second dissociation reaction. And instead of the hydronium ion concentration being a 0, no, from the first step, we have a concentration of hydronium ion. And so we have to put what were the equilibrium values from the first ICE table. They are now the initial values of the second ICE table for the second dissociation. Does that make sense?
Yeah.
Okay, so we're moving on. Second step, change. And your textbook tends to now go to, I believe, Y, because they're trying not to confuse you. And we're going to get plus Y, plus Y, plus Y. We're going to get a Y here. We're going to get a Y here. Oh, nope, I screwed that up, right? I'm going to get 9.4 times 10 to the minus 5th plus Y. And then the 9.4 times 10 to the minus 5th minus Y. And you're going to take a look at that unbelievable second Ka and realize that, yeah, Y is negligible. All right.
Oh gosh.
Oh, gosh. All right.
Does that even exist?
It exists and we can actually measure it, guys.
Whoa.
Okay. But you can see that, oh, golly, the 400 rule certainly is in effect, which, how much farther can it go, Daniel? When we get to the KSPs, there are KSPs that are like 10 to the minus 39.
Oh boy.
It can go, it can really go. It's a little unusual. But, you know, the bottom line, what that second Ka says, guys, is, oh, my goodness, the hydrogen sulfate anion hates to lose that H plus. It didn't even like losing the first one. Now it's losing a second. Yeah, it's not cool. All right. But you
Doc,
can see that, what's that?
could you go back to the first ICE table for this problem? The
can.
first ionization.
Yeah, give me a sec. Because again, my stupid, there's going to be an annotation on top of it. Oops, it's gone. Hang on. I'm going to have to get that out of there.
So when we set up the ICE table, we're just setting Ka1 equal to the equilibrium, like what we
First
get for
one.
equilibrium. Yeah, for the first one, Ka1.
Yep.
And we solve for X that way.
Yep. And so you solve for X that way. All right. Did that make sense?
Mm-hmm.
And that's when, you know, yeah, so it was the minus X, the plus X, the same old drill, but you're right. You were, because this is the first H plus coming off, you do have to use Ka1. All right.
Mm-hmm.
X squared over 0.1 because the 400 rule is in effect. All right.
So we can neglect the
We can
X.
neglect X with respect to the 0.1 without a doubt.
to the 0.1.
Remember, that's always what we're doing, is we're saying, is X negligible compared to the initial concentration?
Mm-hmm. So I'm looking at it on the PS assignment, and the first K1 for a problem that's really similar to this example is to the -3rd power. So it's that one's, we can't neglect that one.
Oh, double check yourself, because what's the original concentration?
1 molar.
Right. So 1 molar, and again, so run it so you don't have to waste your time.
Mhm.
Our only concern is X less than 5%? Is X going to end up being less than 5% of the original concentration?
Mhm.
And that rule of 400 will work for you. So
Okay.
that one's pushing it on the problem solving assignment, but it's
Yeah.
1 molar, right?
Yeah, 1 molar.
1 molar divided by, what was it? What's the
Uh,
K?
1.4 times 10 to the negative third power.
Times 10 to the minus third.
Mhm.
And I get a factor of 715,
Oh yeah.
right?
Yeah.
So we're safe.
Okay.
All
Thanks,
right.
Joe.
Always make the comparison between that initial concentration of the undissociated substance and the K.
Mhm.
And it's not going to go wrong, all right?
For the for the second trial, are you still using the initial concentration of 1 molar?
No, because it's changed.
So which concentration are you using?
That's the thing. You have to use the equilibrium concentration from step 1 to be the initial concentration in step 2.
Which is the X value you get from the first
Exactly.
Okay.
Okay. That's how that works. Whatever you create, however much hydronium and first conjugate base you create in the first step, that's what you use in the second step.
Okay.
Yeah, Daniel, I'm not quite sure why today I'm having to erase everything. Again, I think I dorked something in the setup. I could attempt to just, if I go, yeah, that's not going to work. I can also, though, I can just clear my drawings. And that for now, again, guys, I am so slow at compensating for all this technology crap that I don't want to waste y'all's time. So I just need to clear the drawing and get on with my life. And then, yes, I will just deal with it. We'll get it figured out. I hate this crap. But so, yeah, to address your concern. So here is that second ionization.
Yeah.
And the initial values are what we solved for in the first ionization.
Mhm.
Now, sometimes people have an issue here asking which direction is it going to go? Well, our ace in the hole is still the fact that we have 0 concentration of one of the products, which means it's got to go to the right.
Yeah.
Okay. So in terms of the sign,
Mhm.
plus y, and we get down to here, and you can see, I mean, essentially, it's just going to be 9.4 times 10 to the minus 5th, right? Because 9.4 times 10 to the minus 5th minus y is essentially 9.4 times 10 to the minus 5th. 9.4 times 10 to the minus 5th plus y is still essentially 9.4 times 10 to the minus 5th.
Mhm.
And then all we're having to worry about down here is that, whoops, I got a little issue there, is that y.
Yeah, and we're solving for y.
And we're solving for y, and check this out. Life gets really easy all of a sudden, because Ka2 equals 1 times 10 to the minus 19.
Mhm.
Which equals about 9.4 times 10 to the minus 5th times y over
Oh.
9.4 times 10 to the minus 5th. That second dissociation constant is so small.
Yeah, literally.
That your concentration of sulfide in this example is now equal to the second Ka.
All right. All right.
All right. This
So
works.
what happened?
Oh, go ahead.
What would happen if we didn't use the hack for this one?
Oh, Lord.
Okay.
You'd just be in quadratic hell. Right?
But the values would be slightly different, right?
Oh, but so slightly different. I mean, look at the delta between between that initial concentration and that Ka.
Yeah.
You'd have to have 15 sig figs for it to matter. And we're working with 2 sig figs,
Right.
right? So we really don't care.
Okay.
Does that make sense, y'all?
Yeah.
All right.
Yeah, I'm trying to get through it on the problem solving assignment right now.
Okay.
It does make sense though.
It should come out quite pretty. That's that. Yeah. This was me. We got that for this. So you know that the hydronium ion concentration, and again, look at, we did for both steps, so to speak, we solved for a hydronium ion concentration. But seriously, guys, look at this. The hydronium we made in the first step was 9.4 times 10 to the minus 5th molar. The hydronium ion, the additional hydronium ion concentration we produced from the second step was 1 times 10 to the minus 19th. We would literally need 15 sig figs for that to make a difference to our answer for the hydronium ion concentration. So the hydronium, sure, it's the sum of the 2 steps, but come on. 9.4 times 10 to the minus 5th plus, we did make a little additional. But it's in the noise level. So your hydronium ion concentration is this, guys. And if they're asking you for a pH, you're just going to take the negative log of that. And we're going to get whatever we get. What was it? 9.4 exponent 5.
I got 4.03.
Yeah. We're going to go with 2 sig figs. So it's 4.0. It was 4.02 something, right? 26, 27. So we're going to go 4.03. Yes, you could go ahead, just amuse yourself by taking the negative log of 1.0 times 10 to the minus 19th. And you find out that our pH would be a pH of 19. Yeah, I don't think that is contributing to the acidity of the solution in the end.
Yeah, no.
No. So that hydronium came from the first step. That sulfide came from the second step. It's unbelievably tiny. It always is. The concentration of that second anion, that second conjugate base that is formed, is always equivalent to the second Ka. That's the bottom line. And if you have to do this a third time, it just gets worse and worse and worse and worse.
Oh, I see.
All right. Are you ever going to see me asking you to do all 3 Kas from phosphoric? No, it's too much. It's just too much, and it's not going to make a difference. Sometimes it does, but usually no. Oh, there's Bob. Everybody say hi, Bob.
Hi, Bob.
Can you
Hi,
hear
Bob.
Bob?
Hey.
Yeah,
Yeah.
he's down there doing his thing. Telling the fox to go away or something. So we do that. What do we got there? Oh yeah, hi Bob. We did it. We already got this far. This is just the answers. All right. So when you go back and you need to look again, I have left the sapling answers in here. and we get there and we get there and we get there. We did all this already. We get to the end. We find out our sulfide is 1 times 10 to the minus 19th to 2 sig figs. We find out that our pH comes exclusively from that first ionization. All right? And that's the way this works. So now you should be able to kick through that one on the problem solving. And now there's a couple other things we need to do. Is everybody with me?
Yep.
Mhm.
All right.
Yes.
Acid-base properties of salts. Boy, different textbooks do this in different ways, guys. So I've kind of done a compilation of slides here. Not all these slides are from IGC, because I think some of the IGC slides were clear as mud, to be blunt. But just a couple of things. I'm just going to talk through most of this. Salt. What is the definition of a salt? A salt is an ionic compound that it neither doesn't contain either H plus or OH minus. But that doesn't mean that salts can't be acidic or basic. And this is kind of an interesting topic. It feels a little academic in nature, but it can be very, very practical depending on what you're working with. So you can have salts that form neutral solutions. You can have salts that do not form neutral solutions. And when I say this is in water, all right? Michael, could it also come from the rock halite? Or yes, right? Geologists care about this desperately because they're, analyzing samples for ionic compound content, for salt content, in order to figure out where it came from and how old it is and how it formed. And these different salts, when dissolved in water, may or may not be neutral. Guys, here is the only time when a salt is neutral in water. They have to have been formed from the reaction of a strong acid with a strong base. In other words, the cation has to be from a strong base and the anion has to be from a strong acid. Well, yes, Michael, more like geochemists, but why else would you be a geologist unless you wanted to do geochemistry? I do not know, but I might have a little preference there. So I give you an example right off the bat. Sodium chloride is neutral because the sodium ion is the counter ion of a strong base, and chloride is the counter ion of a strong acid. Counter ion just means the opposite ion, all right? Remember a while ago, like last week, I said, we talk about strong acids and bases, we talk about weak acids and bases, but there's a huge range of weak. And then we talk about acids and bases that are so weak as to be negligible. All right, so this is what we're finally looking at. Chloride is such a weak conjugate base that it's not basic at all. Sodium is such a weak conjugate acid as that counter ion, so as not to be acidic at all. And so all you really got to do there to spot these neutral salts is have those strong acids and bases memorized. The bigger issue comes down here, and that's more what I want to walk through. All righty. As I attempt to go on. Come on, machine. Yeah, I've got to figure out my own technology. I really do. So here's your reminder list. All right, strong acids. I took H2SO4 completely out of the table because it's just a pain in the neck. Because it's diprotic and that second H plus is actually a weak acid. So just don't worry about it. But these are the anions and the cations that you're trying to spot. The chlorides, the bromides, the, oops, sorry. My pen did not take effect. The chlorides, the bromides, the iodides, the nitrates, the perchlorates, the chlorates, all right? And then over here, all those group 1A and group 2A ions that will accompany the hydroxide.
Are those all the ones we need to memorize?
Those are the ones you just need to have in your head. Yes. Okay. Because it makes your life really easy. It should make your life really easy, at least. Hang on, come on, mouse. So, anions of strong acids and cations of strong bases have negligible acid-base characteristic. But cations, and here we go, and this sounds even terrible to say, so I'm going to encourage you to write the equations. Cations that are conjugate acids of weak bases are actually acidic. The classic example is ammonium. He is, and this is why you've got to have these conjugates, this concept of conjugates, you got to have it in your head. Ammonium is the conjugate acid of ammonia. All right. Well, the conjugate acid of ammonia, when you dissolve it in water, look at what it does. You take it. So it's the acid now. The water's the base. You get your conjugate base. And oh, look, you make hydroxide or hydronium. And remember, that's what you're looking for. You're looking for, did I make hydronium or did I make hydroxide? This is how we're defining acidic or basic solutions. If you make H3O plus, measurable amounts, it's acidic. If you make OH minus, it's basic. And so you're constantly having to write these dissociation reactions in order to know what in the heck you're working with. You can also brute force it. Anions that are conjugate bases of weak acids are basic in water. Cations that are conjugate acids of weak bases are acidic in water. But you know, I even when I say that out loud, I start getting confused personally. But I can write the reactions. Look, this is acetate. It is the conjugate base of acetic acid. You dissolve acetate in water. It pulls a proton, it pulls an H plus off of the water. We end up making the conjugate acid and a conjugate base. But what's important is that that new conjugate base, that's hydroxide, and that is how we measure basicity. Think pH and think POH. That's what we're measuring. That's what we're looking for. All right. And so we just kind of start walking through this. So these slides are not from IGC. Salts that yield neutral solutions. Take a look at this. Here's the salt. It came from a strong acid. It came from a strong base. So you get sodium nitrate. The sodium cation is the counter ion of a strong base, which means its characteristics are negligible. The nitrate came from nitric, a strong acid, which means its characteristics are negligible. Neither of them will dissociate in water. That's the point. The acid and the base were so strong in one direction that it won't go in the opposite direction. It's not reversible. So you have a counter ion of a strong base combined with a counter ion of a strong acid, and you have something that is neither acidic nor basic. The pH you're going to get from that solution is going to come strictly from water. It's going to be a pH of 7. Okay?
So this is the definition of a of a neutral solution.
Yep.
Okay.
All right. The neutral solution. Oh, come on, machine. So now we got to look at these others. So now look, there's acetic acid. It's just been drawn in the other form. It's been drawn in the organic form. All right. The ionizable proton there, the ionizable H plus is that one. So what we're making in the solution is this salt. So it consists of the anion of a weak acid and the cation of a strong base, which means this thing's negligible. And the only thing we're worried about is what does the acetate do in water? What does the acetate do in water? And so you have to rewrite the equation. And move on. There's the equation of importance. The acetate will turn around and dissociate, or well, and not dissociate, react with the water to be back in equilibrium with the acetic acid. But look at what the other product is. This is a KB expression. So the weak base makes hydroxide. So salts that yield basic solutions. If it is the anion, oh, and Amazon's delivering something, so say hi, Bob. So since the acetate is the only thing with any acid or base characteristics, you dissolve it in water. No, Bob is just real protective. He hates delivery guys. That's his job, right? That is, you know, he barks. They come to the door. He barks. They leave. His job is complete. That's what dogs are supposed to do. What they're there for. Besides other things. But he's protecting his pack. Anyway, so we're looking at this anion of a weak acid. Throw that anion in water, and by gosh, it makes hydroxide, which makes this solution basic. That's what you need to focus on. And now, of course, we do the opposite. We go with a salt that is formed from a strong acid, which means that that chloride's not going to do anything in water, and it's only going to be the ammonium that has any acidic properties in water. Come all the way down to here. This is what's important. You take that ammonium, you toss it back into water, and now it's in equilibrium with its conjugate base. But focus on this. The other product is hydronium. Focus on the hydronium or focus on the hydroxide. You calculated pH from the hydronium ion concentration. So now this is a Ka again. So yeah, it's going to be acidic. The ammonium's going to react to produce the hydronium, but the chloride's basic properties are so negligible that it won't do anything in water. It just sits there and stares at you. That's why in 111, we classified them as spectators. It's because they don't do anything. They just sit there.
Oh,
Does that make sense?
yeah.
Okay, that's essentially a spectator is something that is right in terms of acids and bases. A spectator is such a weak acid or such a weak base that it is negligible. It has no characteristics. Its characteristics are so weak that the acid-base characteristic of water overwhelms it. That's probably the best way to say it. So, you know, this is back to being a sapling or an IGC example. They said ammonium nitrate, right? We've got it in our supply room. Is it acidic, basic, or neutral? Oh, and there's the world wanting me. Hang on. Shut up, world. Yes, I still have a landline. Isn't that weird? I must be really old. I must be really old. Anyway, and it's all spam, but that's okay. Anyway, so you take a look. Just look, and hopefully you will notice. You're like, oh, nitrate. Didn't that come from nitric acid? Isn't nitric acid a strong acid? So doesn't that mean that nitrate has no basic characteristics whatsoever? Don't worry about it, right? Don't worry about it. The only thing we're worried about is the ammonium, which is the conjugate acid of a weak base. Toss it in water. It's in equilibrium, again, with its conjugate. But don't focus on the conjugate. Focus on the fact that the other product is hydronium, and that is how you calculate a pH. If you make hydronium, the thing's an acid. Okay?
Yep.
And ignore the nitrate. That will get you through all those delightful sapling questions. There is one last complication. What if both ions are conjugates of weak substances? And you're like, really? Do we have to do this? Yeah, kind of. All right. Just so you know, because look, what some of you people want to do for a living, you're going to be dealing with buffer solutions. You're going to be dealing with all these weak acids and bases because that's what's in nature. So you do have to have an appreciation for this. You are not going to fail this class if you can't get this problem right. But you're going to look at both of them. And the ion with the stronger property will predominate. All right? The example they give in sapling, or sorry, the example they give in IGC, notice I use sapling and IGC interchangeably, is this ammonium phosphate. All right? The ammonium is the conjugate acid of a weak base. It's conjugate acid of ammonia. So we've got NH4 plus mixing with water to do its thing. Now look at this. If that's the acid, then the water's the base. You're going to make some more ammonia, and you're going to make H3O plus. So the ammonium is acidic in water. Look at the phosphate. It came from the hydrogen phosphate ion. So yeah, it should be able to pick up a proton, make HPO4 2 minus, and yes, I'm being lazy and leaving all the AQs out, okay? But look, so that makes it the base. It just made its conjugate acid, which means that this is the acid, and it has to make its conjugate base. And so what you have are competing anions, or competing ions. The ammonium is making hydronium. Bob, dude, stop. The phosphate is making hydroxide. Okay? And the question is, who wins? Who predominates? You need the values of the Ka and the Kb. The bigger one wins. And that should make sense. If the ammonium is a stronger acid, then the phosphate is a base, then the ammonium is going to win. If the phosphate, as is this case, is a stronger base than the ammonium is an acid, then the base is going to win.
And that's only determined experimentally, right?
That's only determined, not so much experimentally, but with a big honking sheet of Kas and Kbs.
Okay.
You're literally going to pull the Kas and Kbs out of the appendix and make the determination. All right?
Okay.
But that will get you through all of those. let me get, dun, 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 just killed that. Here, I pulled one more just so you guys can do it, and then all the sapling questions should be fine. Here's ammonium fluoride, same drill. Who predominates? Well, ammonium is a conjugate acid, right? So it's a weak acid. It's going to make hydronium. The fluoride is a weak base. Remember, HF is not a strong acid. HF is a weak acid. We'll very briefly talk about why shortly. So what you need are the numbers. You need the Ka for the ammonium, right? We've already written that equation. And you need the Kb for the fluoride. And now all you do is compare the two. Who's bigger? Who predominates?
Ka.
Yeah. So even though each ion has an acidic or a basic characteristic, the larger K is going to predominate and determine what the solution reads like. So it's going to be a pH of less than 7. All right? That's all you got to do. That's all you got to do. It's all you got to do. Those seem very mysterious at times. Oh, but here's what we need. All right? Because Sophia just asked, well, do we do it by experiment? And I said, no, go get them off the tables in the appendix. And you're going to find that some numbers are missing. But the good news is, and I'm not really going to do the derivation, for any given conjugate base pair, if you know the Ka of the acid, you can figure out the Kb of the conjugate base. So you will see that there are lots of numbers missing in the appendices. But there's the relationship. For any conjugate pair, Ka times Kb is going to equal Kw for whatever temperature you're at.
What does the W stand for?
The water dissociation constant. You remember what it is?
Dissociation constant. Oh, is it 1 to 10 to the negative 14th?
Uh-huh.
Okay.
All right. It is a
Oh, yeah.
constant. And again, remember, for academic purposes, we're always at 25 degrees. So it's always 1 times 10 to the minus 14. And that's what they're always reported as. Always, always, always. For those of you who don't believe me, who love the math, blah, 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 there's the derivation. And you're like, yeah, don't care. And that's fine. For those of you who do care, there's the derivation. All we did was set up the Ka for a generic acid. We set up the Kb for its conjugate base. And you realize that, well, by son of a gun, yeah, it's just this. All right. So you can always use it. And that makes your life really easy because there's several questions there on that problem solving assignment that I simply ask you. I say, oh, here's the Ka for the weak acid. What is the Kb for its conjugate base? And then I make you do the whole Kb isotable thing with the conjugate base.
And we use the Kw for all of them.
Yeah.
Okay.
All right. Kw is just 10 to the minus 14. So if you have a Ka, you can calculate the Kb of its conjugate. If you have the Kb, you can calculate the Ka of its conjugate. Now, it does have to be the conjugates, right? You can't be goofing around with unrelated acids or bases. They've got to be conjugates. All righty?
Yeah.
Yeah, that makes life easy, I think. That's what we're trying to do, right? To make life easy, we think. So, right, I mean, seriously, if you have the Ka of formic acid, what's the Kb of its conjugate? Well, Ka times Kb equals KW. I think you can rearrange and solve for that. I'm pretty sure you're capable of that. So the KB is equal to 1 times 10 to the minus 14 over the 1.7 times 10 to the minus 10. And we get, whoops, 10 to the minus, no, 10 to the minus 4, sorry. And we get something along the lines of 1 times 10 to the minus 10. I hope.
Where's the 1.7 coming from?
Oh, from the problem itself.
Oh, let's see.
Yeah, they got to give you one or the other. They got to give you one or the other, and then you can calculate the conjugate. Okay?
So then 10 to the negative 14th is the numerator, the KW.
Right. So KB for any conjugate base is going to be KW divided by KA.
I
Okay?
got 5.9 times 10 to the negative 11.
Yeah, I'll buy that. I said it's on somewhere on the order of 10 to the minus 10, but you got to take a look at the coefficients to see how big that is. And it's on the next slide. Yep.
Cool.
All right. So you can always get those. And that's why don't get intimidated if you're being told to go to a table to look up a KA or a KB and you can't find it. Well, find the constant for the conjugate and calculate it yourself. Okay. Oh yeah, this was just all right. Look, this turns into tedium. It's just another example. Determine the pH of a 1 molar solution of sodium acetate if the Ka for acetic acid is 1.8 times 10 to the minus 5th. Well, this is a Kb problem because this is a weak base. So the reaction you're doing, sorry, that used to be a 2, is this plus water is in equilibrium with the acid plus take a look, if this is the base, again, if this is the base, this has to be the acid. So now this is the conjugate acid, and we're about to draw the conjugate base. So this is a Kb problem. Kb is going to be equal to this concentration, the acetic acid. And again, notice, yeah, you guys kind of have to get used to some of these formulas for these weak acids and weak bases. But you'll also notice that most of the time we have you work with a limited collection of them. Acetic acid gets used all the time. Ammonia gets used all the time. Hydrofluoric acid gets used all the time. But you're looking at a Kb expression. And you're like, wait, but I don't know the Kb. Oh, yes, you do.
Yeah.
Get it from the Ka. You're going to take 1 times 10 to the minus 14th, and you're going to divide it by 1.8 times 10 to the minus 5th.
Mm-hmm.
And we're going to get whatever we just said we got. All right?
So we're ignoring the sodium.
Because the sodium is the counterion of... The answer is yes, Sophia. But
Okay.
it's because the sodium is the counterion of
Strong base.
a strong base.
Okay.
This is why, seriously, guys, you need to be so comfortable with those strong acids and those strong bases. Because, right, you get concerned. You're like, wait, what about the sodium? Oh, wait, never mind. It's the counterion of a strong base. It's like getting all worried about the chloride. Oh, no, what do I do with the chloride? Nothing. It's the counterion of HCl. So it has no basic properties. well, they're so negligible, we don't care. Okay?
Okay.
Okay. Yeah. No, remember, I harped on you guys. Well, those of you who took 111 with me and anybody else who took 111 with anybody else, right? We sit there and we harp on you guys about memorizing the Strongs. And this is partly why. It just makes your life easier because, you know what to do with the Strongs. Can I ignore them totally? So we move on, and I think the answer's here. It's just another ice table, guys. Ice table, fill in the ice table, minus x plus x plus x. Going to be negligible. Yeah, we have to solve for KB. But you did that. It's 5.6 times 10 to the minus 10. You've got your lovely ice table. Yes, your Ka is much, much, much smaller than 1 molar. So the 400 rule, the hack is in effect. Everything's good. You solve for X. Remembering that from the ice table, X is hydronium. Right?
Mhm.
So you're ending up solving for the hydronium ion concentration. You can calculate a pOH. And then you can, to get to the pH, because it is ultimately what they asked you for. You're going to take your pOH, subtract it from 14. I've talked about these sig figs before, right? The sig figs on the 14. I was always taught when doing this subtraction, if I was doing pH and pOH addition or subtraction, I was always taught to treat the 14 like it was exact. I have gone through all the sapling problems. Sapling does not treat it like it's exact, guys. Do you see how many sig figs they gave the 14? In the sapling problems that I have assigned, every time they need you to use a pH or a pOH and do this the addition or the subtraction, they do the 14 to 2 decimal points. I went through and I double checked every single time. If you have to subtract from 14, they're taking the 14 out to 2 decimal points. If there's less in your pOH, well, then you have to go with, if there's only 1 decimal point in your pOH, well, then you have to follow those sig fig rules. All right. And only report to the tenths. But they're always treating that 14 like it's got 2 digits to the right, which is fine. It works out fine. And they're pretty, I made sure, what I thought you said was, 14 to 2 decimals. Yeah, 2 decimal places. All right. To the right. It's just how they treat it in all those homework assignments. And they're pretty, I ran through all those problems. They're pretty kind in terms of if you report 3 digits to the right because you thought it should be a 3 sig fig answer, on a pH or a pOH, they're still giving you credit for it, but they're going to tell you that their answer only went to 2 digits to the right on the pH or the pOH. All right. So don't get too stressed about that. I did double check on that. Right. You got 9.38. Okay. Fine. Sapling's going to give you credit. So you're not going to have to worry about that. And that does depend on where and when you rounded. All right. And also realize that 9.38 and 9.37, what's the percent error in that? 0.01 out of 9.37. Come on, the percent error there, even in the pH, is 0.1%. Oh, same deal. On the exam, I'm looking at your work, guys. Okay, I'm watching your work, and I will make sure, you know, the way this exam's going to work, some of it's going to be sapling, but I will vet every single one of those problems. All right, for any of those multiple choices or fill in the blanks. And then, oh yeah, I'm going to throw some obnoxious worksheet at you, and have you sit there and do it at home. But I'll be able to follow your work and figure out if you got that pH from, you know, rounding in step 3 or whatever. Yeah, that's not going to be a big deal at all. Okay? Don't stress about that. We got many, many more things to stress about than that nowadays, don't we?
Yeah.
Yeah. Yeah. It'll all be good. But that takes care of the salts, okay? Everybody still with me? I don't even know what time it is. Oh, my machine.
Yep.
Okay.
Mhm.
Look, 16.8 and 16.9, not my favorite topics, to be blunt. So I'm going to run you through them really fast. Yes, translation. How much does she care? Not a lot. Not a lot. I'm much more interested in the math. This is very qualitative. Why are some acids stronger than others? Well, you know, why are some strong? Why are some weak? It depends on a couple different things. All right. Obviously, the stronger acids, I mean, you can read the darn slide. Okay. Stronger acids ionize to a greater extent, giving a higher concentration of H+. Fine. In water, there's something called the leveling effect. And that's why we have that whole collection of quote unquote strong acids. And we don't tend to differentiate. They're just all strong. If you put them in a different solvent, they would, in fact, ionize to different extents. And you can differentiate, even in that list of strongs, who's the strongest. I'm not going to make you do that. That's a 300 level, 400 level analytical or quant issue. Okay, yeah, and it's kind of because they feel like it, sort of, Daniel. But realize that you should have noticed by now, some H's in some molecules aren't ionizable at all. And we use our little cheats to figure out which ones, okay? But if you really want to know, I know you don't, but I'm going to quickly do this. We do have to actually differentiate the binary acids and their trends from the polyatomic, from the acids that come from the polyatomic anions. The binary acids are pretty easy to walk through. It's all about bond strength, size of the anion, and electronegativity. If you do have the actual bond strengths, the bond energies, the weaker the bond between the H+ and the anion, obviously, the stronger the acid. And so you can, in solvents other than water, contrast HI to HBr to HCl. Yeah, in water, they're all strong. In sulfuric acid, no, they're not all strong. Only HI and HBr are strong. But it corresponds with the bond energy. Weaker the bond, easier it is to make H+. More H+, it's going to come off. In water, they're all equivalent. But notice that the HF on this number, or on this slide, because the HF's bond energy is significantly higher, that's why it's weak. It does not ionize 100% in water. Fine. So you can look at that. Again, if you don't have the bond energies, you can look at the size of the anion, and you can look at the electronegativity. Now, they're kind of competing effects, though. And I like, personally, that, boy, Sapling gets really fancy with their explanation. The size of the anion explanation is pretty straightforward. That's why I've gone all the way, just right straight to this table. And you can see the bigger the anion, the more readily dissociated the H+ is. The bigger the anion, The bigger the anion, the weaker the bond. Because the H is so tiny, it would like to, if it's going to bond closely, if it's going to bond well with the anion, it would like to be about the same size. It would like the anion to be about the same size as it. So the bigger the anion, the crappier the overlap. So the easier the H plus comes off. The other issue is electronegativity, and it does seem like that should be an opposite trend. But here's the thing, and here's the thing that Sapling does not make super clear, in my opinion, if I go back. The two main factors affecting bond strength or affecting acidity is the size of the ion if you're in the same group, or the electronegativity if you're within the same period. So here's what these competing effects look like. If you're looking at electronegativity effects, you're looking in the same period. If you're looking at anion size effects, you're looking in the same group. So yeah, the HF bond, F is really electronegative, but the F is so small, the F minus is so small, the overlap is so good that the bond is stronger. But you can see it's all leading down to HI down here, who has a huge anion, and the I is not super electronegative. The I is not super electronegative, but the anion is so big that the bond dissociates readily. There's going to be a few Sapling questions. The homework, I almost never ask about it on an exam, to be blunt. To be blunt, I don't usually ask, but some people want to know. So now you know. The effect when you of acid strength when you have a polyatomic anion is mostly electronegativity. They give and they do a couple of things here with the acetic. Please do notice there's only one ionizable H plus on that acetic acid. There's a total of 4 H's, and the question is, why do these guys not come off? Well, because this is a nonpolar bond. All right, the overlap between the C and the H is awesome. Those things aren't acidic. The only one that's acidic is the one out here, because the oxygen's really electronegative. So the environment over here is more electronegative. So it doesn't mind this H plus coming off as an H plus and the rest of this anion staying as the polyatomic anion. That's the bottom line. If you want this molecule to become even more acidic, what you do is you need to make this anionic part of it even more electronegative. And that was their point on this slide. It took me a while to figure out what point they were trying to make on this slide. It is kind of cool. If you start replacing those non-acidic H's with more and more and more electronegative atoms like chlorines, the acids get even stronger and stronger and stronger. Right, and yeah, Daniel, it's not a bad way to look. We look for the H that can make a hydrogen bond. Yes, but it's usually an H attracted or attached, bonded to an O. It's almost always, because all of those oxoanions, next slide. All these darn oxoanions, I'm going to go all the way to here. There we go. Almost every single time you see these acidic protons on these acids with polyatomic anions, it's almost always the H that's directly bonded to the O, which again, yeah, it falls under hydrogen bonding. All right, but it's just more that this see if I can draw. Whoops, this makes a great anion. This makes a great anion. And that other weird one, isn't that one awesome? It's some bizarro, it's diprotic. Makes a great anion. The more O's you have, the more electronegative, the more negative that anion becomes. And so the stronger the acid becomes. Which is why, whoops. Yeah, me and technology, guys. Gotta hate it. Which is why this trend works like it does. The more O's on the polyatomic ion, the more electronegative that environment is. So the stronger the acid, the more likely that that H plus is to come off. And so you see this trend. That's why the hydroiodous acid, hey, I could name it. The hydroiodous acid is weak. Hypoiodous. The iodous acid is also still considered relatively weak, but stronger than the hypo. Then we get to the iodic acid. It's not quite considered strong, but it's a pretty large Ka. I think that Ka is like 10 to the minus 2, 10 to the minus 1. And then we get to the hydroiodic, and it's pretty strong. So more O's on the polyatomics, stronger acid. That's the bottom line. And so, yeah, I consider that to be pretty boring. What else have I got? Oh, for those of you who are going to take organic, 5 minutes or less on Lewis acids, okay? Then we're going to take a short break and come back and do a few buffers if everybody's up for it. Lewis acids and bases, the most global definition of acids and bases. Instead of having the acid be an H plus donor and the base be an H plus acceptor, now the base is an electron pair donor and the acid is an electron pair acceptor. Why do we need this? Organic chemistry. All right. Look, this guy doesn't have any electrons. He would love a pair. This guy has a non-bonding pair. He would love to donate them to the guy without the pair. And again, Lewis acids and bases end up being the most global definition. So all the Bronsted acids and bases are Lewis acids and bases. All the Arrhenius acids and bases are Bronsted acids and bases. So Lewis is by far the most global definition. You can read this later. The only thing is what happens in Lewis acid base chemistry, instead of the H plus just getting passed around, we end up making what are called these Lewis adducts. You literally make a bond. The Lewis base, who has the non-bonding pair, and the Lewis acid, who has the empty space. Remember, boron trifluoride does not have to satisfy the octet rule, but if he reacts with a Lewis base, you can actually make a covalent compound. But both of the electrons in that bond came from one molecule. They weren't shared equally. Both of those bonding electrons came from the base. So it's considered a covalent bond, but it has a different name. It's called a coordinate covalent or dative bond. And we don't have to be in water for this to happen. That's the other reason. So the most global definition of acids and bases is the Lewis definition. The bases donate an electron pair, the acids accept an electron pair. And so there's a handful of sapling questions. And they ask you, are these things Lewis acids, Lewis bases, or neither. All you're looking for is non-bonding pairs or the ability to accept a pair. If you have a non-bonding pair that you can donate or share, I shouldn't say donate. If you have a non-bonding pair that you can share, you're going to be a Lewis base. If you have the ability to accept that non-bonding pair, you're going to be an acid. If you're happy and covalent as you are neither. So you can pretty much just go through these. Most metal cations are considered Lewis acids. Most metal cations are considered Lewis acids. So this one would be a Lewis acid. Now, if you think about methane, he's happy as he is. Satisfied, octet rule satisfied, life is good. So he doesn't care. He's neither. He's neither acidic nor basic. Chloride is perfectly set up to donate a pair. So he's going to be a Lewis base. Ammonia. Oh, look, we have to do Lewis dot structures again. Ammonia has a pair to share. So he's going to be a Lewis base. Hydrogen gas. He's happy as he is. Leave him alone. He's neither. An iron metal. He's pretty much happy as he is. I wouldn't even ask that one on an exam. But he's pretty much happy as he is. Okay? So he's going to be neither. What you're looking for are those non-bonding pairs. And then you know it's a Lewis base. You're looking for anything electron deficient, and then you know it's a Lewis acid. All right?
Okay.
Okay. I'm going to mute up for a few minutes, switch to chapter 17, or yeah. Well, no, where the heck are we? Yeah, chapter 17, and we'll get on with it. Not, what chapter are we on, guys? 17, right? We just finished 16. Yeah. Come back in, I don't know, what time is it, people?
12:30.
12:30. Come back in 5 minutes.
Gotcha.
All right. And we're gonna run the Henderson-Hasselbalch. We're gonna get going on the buffers. I am not gonna titrate today. We'll do it on Thursday. All right.
Okay.
Okay. Yes, they're blood cells. Let me see. Whoops. Sorry. My bad. I'm running two computers here, which is really, you'd think I would be able to run one of them well, but no, not really. It is what it is, guys. There's a reason I enjoy teaching in a face-to-face format. All right. Are we back on? Enough?
Yep.
By the way, History Channel might come by to get some footage of what? Some footage of what? Oh, yeah, stop it. You are. You're the one who's going to keep me sane this next 6 weeks, Daniel. Yeah, I know. I still have a landline. Gosh, what else do I have? I still have a newspaper delivered every morning. It is one of my greatest luxuries is to sit and drink my coffee and read an actual paper newspaper. How about that?
That's honestly kind of cool.
And I will never it's my greatest joy. Not my greatest joy, but to just sit by myself and read a newspaper. God, I love it.
Sounds relaxing.
It is relaxing, and I don't have to try and see it, on a screen that's only 3 inches tall. And then I can, when I'm done, I can line a bird cage or start a fire with it. So, all right. Let's try moving on. All right. Let's see how badly I can screw this up again. All right. At least you'll have stories to tell people. Oh my God, she didn't even know how to do that. Whatever. All right. So we're getting on with it. You've got all this Ka and Kb stuff. Guys, work as many problems as you can. Get comfortable with it. I'm telling you, in my experience, you guys are good at ice tables now. What happens with the Kas and the Kbs now? They'll just say, here, you have this solution in water. Go. And what you have to do is stop and say to your, ask yourself, what's in the water? Okay, so it's a salt solution, but is one of those ions that's making up that salt solution the conjugate of a weak acid or the conjugate of a weak base? All right. And then you've got to write the equation. You've got to write the equation for the reaction of that substance with water. Does it make hydronium as a product? Oh, it's an acid. Does it make hydroxide as a product? Oh, it's basic. And what happens is you forget to do that step. All right. And Daniel, what are you doing? Oh, yeah, we got to bring some. Yes, we need some humor. We need as much humor as we can possibly get. If I'm the one providing the humor because you think I'm totally inept at all this technology crap, well, good for me, right? You should see some of the stupid videos that we made to do some of these labs with, Professor Swamanath there titrating for you. You should see the goofy ones of me doing the 101 stuff. But, we're doing the best we can in very strange times. So, by the way, is everybody healthy?
Yeah,
Yep.
I'm healthy.
For now.
For the most part, still now?
Just so bored at my house.
Sure.
So bored. I'm actually not bored because I'm frantically trying to do all of this because you cannot imagine how much these PowerPoints have to be changed. And you can see it's still not working the way I want it to work. By the time we're done, I'll probably be like, ooh, that worked well. I'm like, oh, great. Day 2 of week 16, and I finally get it right. That's life. It is life. And again, I will reemphasize for anybody who's on right now, because I can't see how many of you are. Oh, God, you're all on. God bless you people. Wow. Anyway, if you lost your job, if you're laid off, Nova's doing everything they can. I don't know if you saw the announcement of they're doing all the emergency grants. Do what you got to do. You got to eat. You got to buy your prescriptions. You got to do what you got to do. Ask for help. And yeah, let's inject some humor into this, Daniel. All right. Because this is just rough on people. I'm sitting here very grateful. I get very cranky at the technology, but I'm very grateful for what I have. You're more worried. What? I'm honestly more worried about the A. You want an A? Are you talking about the class? Keep demonstrating competence, people. Keep uploading your work. All right. Keep uploading your work. Oh yeah, we got food for the week. Yeah, again, like I said, I think Michael and I noted that we tend to have a lot of food in our homes. So yeah, the A is what you need, huh? Okay, as long as you got the food. But don't be afraid. Seriously, Don't be afraid to reach out. The college is trying to provide as much help as possible. And pretty much everything's on the homepage now. So if there's something you need, check in with them. They may be a source. Okay. Anyway, on with chemistry. But you keep getting all these emails that say we care. Well, we do. All right. Trust me. If I didn't care, I wouldn't do this. Especially now. God, this is frustrating. But anyway, let's continue on. All right. We're just going to do the first two sections of 17. So we've got all these weak acids and all these weak bases. There's actually a lot in 17, and Daniel, I'm taking your suggestion now. The heck with it. I'm just running the PowerPoint pen, and we'll see if that just makes me happier. Okay. But I'm just going to talk about what a buffer solution is and why you care. All right. And how to set them up, because things change. The way you look at it, things change a little bit right now. Why do you care about a buffer? First things first, what in the world is a buffer? A buffer solution, and again, we're an aqueous solution, okay? We're going to be an aqueous solution. A buffer is a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. So we're going to prep them. And we're going to prep them at whatever concentration we need, and we're going to prep them in whatever ratio we need. All right? But this is how you control solution pH, because they resist changes in pH by neutralizing the effect of externally added acid or base. And we got to talk about this thing. All right? The reason you care, because everything's a buffer. Everything biochemical is a buffer. Your blood, right? The pH of your blood, which can't go outside the range. Somebody help me. I always get this messed up. 7.35 to 7.45. Quick, somebody Google it. Or somebody who's heading into the medical field, tell me.
7.35 to 7.45.
Okay, we have to keep, in order for all our organs to function properly. Every organ system has a different optimal pH, and every organ system has a buffer system that helps keep that pH in that range. So we're looking at, and most of these systems operate optimally in only about 1/10 of a pH unit range. All right. Your blood pH goes outside, much outside 7.4, and you've got problems. Things start failing. This is why we care. All right. What's the concept behind it? It is it's this common ion effect concept. And what it really is, guys, is just Le Chatelier. Okay. It's just Le Chatelier in effect. And you guys were all pretty comfy with Le Chatelier. What it is you're going to need a weak acid and its conjugate base. If all you've got is the weak acid, you put it in water, it does its thing, and it makes a little bit of conjugate base, right? That's just the equation. And a little hydronium. Fine. But what do you say you artificially increase the concentration of the conjugate base? So you stress the product side. Which direction does the equilibrium shift to?
The left.
The left. And you suppress the ionization. All right? It's called the common ion effect. All right? Buffers operate under the common ion effect. So they do give you one example of just seeing how it works out. So first, they just want you to calculate the pH of an aqueous solution of nitrous acid. It's a weak acid. That's just going to be a boring Ka or tedious. It shouldn't be, I shouldn't say boring, a tedious Ka problem. All right. But then we're going to mix it up and we're going to apply the common ion effect. And we're going to see how it affects things. So first things first, I'm not even going to run through it, guys. Okay. You got 0.3 molar nitrous acid. It's undissociated. It's unionized. You add it to water. Let's see, just no asking, just mean, oh, sorry. Wouldn't that be a strong base? What, the nitrite? It's the conjugate base of a weak acid. So the question is, how strong is it? Not that strong, because because the nitrous is a weak acid. Its conjugate base is also weak. How weak? We have to see. Kas, Kbs. In fact, you can see there's the Ka for the nitrous. So the Kb for that base is not that big. But, you know, if you just set up this ice table and you find out that the pH, you go down, you do your thing, it's 0.3 molar. Look, the 400 hack still applies. All right. The 400 hack still applies. We do our thing. Whoops, that looks like a typo, isn't it? I didn't catch that before. And you find out that the hydronium ion concentration is about 0.013 molar. Okay? Take the negative log of it, and you find out that this pH is actually pretty low. All right? It's a moderately strong weak acid, so to speak. But now here's the fun little catch. What if we artificially, sorry about that, screwed that up, give me a second. What if we artificially add some of the conjugate base? So now we have this initial concentration of the weak acid, and we have an initial of a greater than 0 initial concentration of one of the products. Again, this question, we did one of these similar one earlier, but I want to emphasize again, you take a look at this and you may question yourself as to which direction this reaction is going to proceed initially. Don't question yourself. There's still no hydronium. Okay? Right, towards the 0. If any of those remember the water's irrelevant, right? If any of those initial concentrations are 0, that's the direction it's gonna go. So you don't have an issue with these signs. All right. And now you get the 0.30 minus y, and you get the 0.20 plus y, and we get a y. And you again ask yourself, can I use the 400 hack? And the answer is yes. All right, 0.2. Let's check it. 0.2 divided by 0.56. Ooh, we're pushing it.
So theoretically not.
Yeah, let's see how this works out, right? So we move on. Because, see, I knew this. They actually took the hack. Notice, they said, oh, we're pushing it, but let's see if y is negligible enough. And they run the math.
So
Check
they
it out.
rounded
go ahead.
357. They rounded 357 to 400 as an idea.
Yeah, 357, does that round to 400? Kind of. Let's see how close it came. All right, this is the one where I hope I left that calculation in. They assumed that they could take the hack, and they simplified that equation because it would have been a train wreck otherwise, right?
Yeah.
Yeah.
That would have just stunk. Oh, I did leave it in. Okay. Guess what? It actually worked. They went back and checked that y was small enough. And they actually did the math. Because remember, that is always the original question. Is x less than 5%? Well, in this case, y, less than 5% of the initial concentrations? And the answer is yes. So now you suddenly realize that 400 hack is actually conservative, which is nice to know, right? That's why I just keep saying to you guys, yes, take the 400 hack. Yes, take the 400 hack, because it's actually conservative, especially for weak acids and bases where these expressions are so simple, where it's always, x squared over something, something, something. So it's actually a pretty good situation. But now if you take a look at the pH, yeah, magic at its very finest. I don't know why textbooks don't allow you to use it. Like I said, I stole that hack from Silverberg and Amateus. Amateus is a full professor at Virginia Tech, just so you know. So when she teaches chemistry, she teaches it out of her own textbook. Whoa, remind me not to take that course. Anyway, but you can see what an effect putting the counter, or the common ion effect, putting a bunch of that weak base in that beaker, you can see how it really, really reduced the dissociation of the acid. You made lots less hydronium just because of Le Chatelier. And this is the great news with buffers. If we put in, what we really like to do is put in pretty much equimolar amounts of the weak acid and its conjugate base, or the weak base and its conjugate acid. If you put in about equimolar amounts, you get, based on the Ka or Kb, you get a very constant pH. And then when you start adding, or nature starts adding external sources of acid or base, pH doesn't change very much. That's the point of a buffer. And so I just give you the examples down below. So you're either going to want significant amounts of this guy with this guy, or this guy with this guy. And these two equilibria, these two reversible reactions, are going to be in effect. All right? And it does amazing things. Here's their cute little graphic of how this works. Think about it. So you have this lovely combination, this lovely mixture of this guy. Oops, I just lost my pen. Come on, pen. This guy. Here we thought I knew what I was doing. So we have about equimolar amounts of the weak acid and his conjugate base in water, aqueous solution. And now nature adds a bunch of that. Adds a bunch of externally added strong acid. But Le Chatelier is in effect. Which direction does this reaction shift? So I've just increased the concentration of one of the products. Which direction does it shift?
Left. Or to
Left.
the reactants.
To make more reactant, right?
Hmm.
Correct, I should say. Correct. Makes more reactant. Consumes the external added acid. Well, look, you calculate pH from the concentration of this. If you added it to the beaker, and all that happened is it shifted to the left and made more weak acid, you haven't changed your pH. And that's the point. If you do the opposite, and now I am going to have to erase some of my crap here. What if I do the opposite and I add, now this one you have to think about a little bit more. What if I add external base? What if I added literally, what if I drank Drano? If I added an external source of strong base, what's it going to react with?
The weak acid.
Nope. What's its favorite friend in the whole world? Yes, Daniel, the H3O plus, because OH minus plus H3O plus makes
Uh,
a couple of waters, right?
mm,
So adding the H plus is also a stressor. What it does is it consumes some of the H3O plus, and it shifts the equilibrium this way. And you make more weak base. But you don't change the pH. You don't change the pOH, you don't change the pH. It is exquisite how this works out for us. Item number 1, though. Which of these could you use? Which of these pairings could you even use to make a buffer? It has to be a weak acid and its conjugate base, or a weak base and its conjugate acid. Those are the only options. So option A, can you make a buffer out of that? Is it a weak acid?
So,
Nope. All right. Nope. That one right off the bat doesn't even matter what the conjugate. Doesn't even matter what the other thing is. It's not a weak acid. You can't make a buffer out of it. Look at C. I'll just go down to that one. Is it a weak acid?
yeah, strong.
Nope. Okay. You see why you need to memorize these? So now you look at this one. And you're like, well, let's see. That's hydrogen carbonate ion. And then let's see. And water, hydrogen carbonate. Sure not a weak, or it's certainly not a strong acid. It's certainly not a strong base. It's kind of good practice for you to go like this and think, okay, let's call that the acid. Let's call that the base. Let's make CO3 minus and H3O plus. Oh, look, it's a weak acid. All right, so here's his conjugate base. And its conjugate base. There it is. Boom, boom. You can make a buffer out of this one. And in fact, that is one of the buffers that keeps your blood buffered. All right, that is one of the blood buffers. The carbonate, the carbonic acid, hydrogen carbonate, CO2 and water buffer system is just exquisite. Oh, and I just saw your answer, your question. Okay, yeah, never mind. Okay, got it. All right. So first things first, don't be fooled by that. What you're going to see, not today, but on Thursday, we can make a buffer using a strong acid or a strong base, but it's a very, very specific process by which we do it. And so I'm not even going to get into it right now, but right now we're just looking at pairings. There's only one good pairing on that list. So here we go. Where am I in this? Yeah, here we go. Look, more ice tables. But the good news is in about 5 minutes, we're going to get rid of the ice table, at least temporarily. All right. We're going to calculate the pH of a buffer containing initial concentrations. Oh, we just did this. All right. We just did this in the previous problem. There's our weak base. There's his conjugate acid. So here's an example of a buffer made from a weak base and its conjugate acid. Fine, whatever. You put in the initial concentrations, you set up the ice table. Which direction does it go?
The right.
Yep, towards the zero. All right, you're getting good at that now, aren't you? So we end up with the minus X and the plus X and the plus X, and we do our thing, and we double check the size of that KB, and everything's going to be fine, right? We're going to be able to take the hack. You're going to do the math. It's all going to be great. You are going to solve for OH minus. You're going to solve for a POH because this was a KB. You're going to solve for that. Fine. It equals X. You run the math and you find out that the OH concentration's what, 2.7 times 10 to the minus fifth. I think I checked that one. I think it's fine. I don't think we have an error. And then you're going to take your 14 minus your POH. Again, Sapling's always reporting 2 digits to the right on that 14. I tend to make it exact, whatever. We're going to be, right, depending on which way you do it, we're going to be off by maybe 2/100ths of a pH unit at most. Don't get stressed about that, okay? So you did the whole ice table thing. Yay, good for you. You're getting very good at that. And now we turn around and Sapling, it actually took me a minute to realize what Sapling was having you guys do here. Now they say, hey, ignore the ice table. Just pretend that you're already at equilibrium, which is okay because we already figured out that X was negligible. Make it easy on yourself. KB equals whatever it was times the concentration of NH4 times the concentration of hydroxide over the concentration of NH3 but let's just put them in like they're at equilibrium. Let's just plug the numbers in. We're going to have to write the OH minus is going to be X. We have the value for KB. We have the concentration of the ammonium. We have the concentration of the ammonia. We're going to rearrange and we're going to solve for hydroxide. And guess what? The numbers are obviously still the same because we'd already said that X was negligible compared to the 0.14 and it was negligible compared to the 0.21. And so essentially what we did is we skipped the ice table. And in many cases, there is no need for the ice table when we're looking at a buffer solution. Because things are ionizing so little, the initial concentrations are a good approximation for the equilibrium concentrations. And it makes your life, but so we can still do the ice, but just fast, right, it's faster to skip it. But now look, it's only for buffers. At all other points, you're still going to have to run that ice table. But if you are obviously working with a buffer, you can skip the ice table. All right? And that's why. So if I can skip the ice table for a buffer, there's all kinds of cool things that happen. Here is your favorite equation in the whole world when you are working with buffers, but it only applies to when you are working for buffers. And I can't begin to tell you how many times students will do too much work or too little work because they're not paying attention to whether the system is a buffer system or not. It's called the Henderson-Hasselbalch. And it is a 3 PowerPoint slide derivation.
What?
Yeah, of everything we've already talked about. So look, congratulations. This equation is on your formula sheet. the pH of a buffer system is equal to the pKa of the acid plus the log of the conjugate base concentration divided by the acid concentration. We can also do it with pOH if you're working with a base, but we'll do that on Thursday. How does this thing get derived? Like I said, it's about 3 PowerPoints. Again, for those of you who want to play with it, knock yourself out. We start with that equation. We set up the expression. We rearrange to solve for hydronium instead of Ka. This is just math. We take the negative log of both sides. We redefine the negative log as the pH. We redefine the negative log as the pKa. And everything's glorious. And we come out with that. But it only works for buffers. Not only do we not have to do the ice table because the initial concentrations are a good estimate of the equilibrium concentrations, but we can do it with pHs and pKas instead of hydronium ion concentrations and Kas. So we can get rid of all those negative powers of 10 as well. It is the most fabulous thing ever if you catch that you can use it. So even better, you're like, well, I'm going to need the molarity of the conjugate base and I'm going to need the molarity of the weak acid. No, not really. If they're in the same beaker, guys, the proportion of the molarities is equal to the proportion of the moles. But it only works in buffers if they're in the same beaker. Okay? And this suddenly gets, again, like Daniel, you asked, so we can skip the ice table, right? It's faster to skip, but we can still do it. Yes. You can still do it. You'll still get the right answer. But oh my goodness, would you rather set up a big honking ice table or would you rather plug and chug into this? If somebody asks you to solve for a pH.
Plug and chug.
Plug and chug, as long as you have an appreciation for the derivation and where it came from, and the only time you can use it is with a buffer, you're golden. But it does mean you have to be able to spot those weak acids and their conjugate bases. You have to be able to spot the weak bases and their conjugate acids. You have to be able to spot this. And so you get problems like this. And this is about where we're going to end today. I'll show you one reversal or one rearrangement of this. But look, they're asking you for a pH of a buffer. Okay, it should be screaming at you, Henderson Hasselbalch. pH equals pKa plus the log of the conjugate base concentration over the acid concentration. It should be screaming at you. Okay. Bob, are you fine there, dude? All right. My dog's making funny noises. It's okay. Only thing they didn't do for you, they didn't calculate the pKa for you. So quick, do it. 1.8 times 10 to the negative fourth. We take the negative log of that. And to 2 sig figs to the right. I get the pKa is what, 3.74?
Yeah.
And this is, look, I mean, take a look at it. It's incredibly straightforward now. pH equals 3.74 plus the log of, all you got to do is spot that this is the formate. So that's the conjugate base. There's the weak acid. So we put the 0.120 in. Again, Sophia, earlier today you said, so I don't have to worry about the sodium. You've got the answer for that, right?
Yeah.
Right, because you know that sodium is the counter ion for a strong base.
Yeah.
So it's negligible. We don't care. And abracadabra, This is about as easy as it gets, guys. Do the math. I don't know what it is. 0.12 divided by 0.17. Remember how I have to do this. It's very weird. I got a 3.59.
Same.
Cool. There you go. There is your buffer solution pH. I know, poor sodium. No one cares about it unless we eat too much of it, and then we all get hypertension. I don't know why that says A. It should say B. I don't think I screwed that up. Regardless, look, it's the same gig. All right. Because the formic acid and the sodium formate are in the same beaker, in the same volume, the ratio of molarities and the ratio of moles are in essence the same. So in it goes. All right. It's wonderful. You do have to stop and ask yourself, are they both in the same beaker? If they are, great. There we go. And because this solution has a little more weak base in it, it's going to be a little more basic. It's going to be a little bit higher than the 3.74. And that's what you're going to see on the next slide. I got a 3.92?
Yes. You got the same.
And that should qualitatively make sense to you. Look, for the pKa, for pH to equal pKa, the ratio of weak base to weak acid have to be 1 to 1. Think about it. The log of 1 is 0, right? So when the weak acid and its conjugate base are equimolar, pH equals pKa. That is the basis of one of the calculations you're doing in that titration lab. All right. If the ratio of base to acid is greater than 1, you're going to get a pH higher than the pKa. If the ratio of base to acid is less than 1, you're going to get a pH less than the pKa. And that's what you see on the next slide. All right, we did a great job. Yay, us. And I've already talked this out. Take a look. If this is a 0, that means the ratio of base to acid is exactly 1 to 1, and pKa equals pH. If there's more weak base than there is weak acid, the pH is going to be a little higher than the pKa. If the opposite is the situation, if we're in the opposite situation, then we're going to get a pH that's a little less than the pKa. And remember, the trend in pKa is the same as the trend in pH. The closer to 1 the pKa is, the stronger the acid is. And so you can do all kinds of cool things with it. Here's the last thing I'm going to do with you guys, and I think we're done for the day, unless people have questions. They're asking here for the relative concentration of acetate and acetic acid. In other words, they want this ratio. That's all they want. Well, all you got to do is rearrange the Henderson-Hasselbalch. So all I'm going to do is say that the log of this ratio is equal to what? pH minus pKa?
Yes.
And if the pH is equal to 4, because it's up here, and the pKa, I already solved for it for you, is 4.74. Then the log of that ratio is equal to a negative 0.74. You are going to raise both sides to the power of 10, right? 10 to the x. And you're going to solve away. And you're going to end up with a ratio. So we'd gotten that far. So you took both sides, 10 to the x, and you end up that this ratio has to be about 0.18 to 1. In other words, the acetate's only about 20%. So you've put, 0.18 moles of acetate in and 1 mole of acetic acid in. And so now you can sit there and you can prepare buffers that have the pH, whatever you want. You're like, I need my pH in order to do my biochemical experiment. I need a pH of 4.0. What you do is you go find an conjugate base pair that has a pKa somewhere close to the pH you want. And then all you would do is adjust the base and acid amounts until you get the exact pH you really want. And that is how people do it in a lab. And I will send out a problem-solving assignment that makes you do it a couple times. You pick your pH, you find an acid-base pair that comes, whose pKa is close to that pH, and then you adjust, you do the minor adjustments with the concentrations, and bam, you're good to go. All right? It's very pretty, and it is really, truly, in the real world, how we do it. Pick your buffer system and adjust the concentrations accordingly to get exactly what you want, right down to the 100th of a pH unit. It is very cool. Buffer capacity and buffer range. Capacity refers to how much external acid or external base the buffer can handle before it falls apart. We'll do a couple of examples of that on Thursday, okay? The higher the concentrations of the weak acid in its conjugate base, the higher the capacity, the longer it's going to take. I call it blowing the buffer up. The longer it's going to take to blow up the buffer. Yes, you can destroy a buffer if you consume all of the weak acid or you consume all of the weak base so that it's not in equilibrium anymore because you're totally missing something. Well, then you're stuck. You've killed the buffer. The other thing is, and they didn't call it this is actually called buffer range. Again, if you're wanting a useful buffer, well, start with one whose pKa is within about 1 pH unit of the pH you would be at. Outside of that, the ratio of acid to base is so large or so small that it's just not practical. So the capacity, just up the molarities and the buffer will last longer and be able to handle more stressors, and get yourself a good range by finding a system that has its pKa close to the pH that you're interested in. And you'll have a very efficient and effective buffer. There's some more examples. I'm going to let you walk through those examples yourself and ask me questions on Thursday. What they've done here is this is just a calculation for the buffer. So just use the Henderson-Hasselbalch. Then they have you stress the buffer. So you are going to need an ice table on this one. And solve it. And then they have you contrast adding strong base to the buffer versus adding strong base to pure water. walk yourself through it. I'm going to put one of these on the problem solving assignment as well. But if you can walk yourself through this, you can do anything I can throw at you so far. And I'm going to stop. I'm tired. I'm sure you are. We all need to go eat lunch. I will set some office hours. The way that's going to work, guys, is I'm still going to be so kill the buffer or kill the water. Yeah, you're going to see. You don't even come close to killing the buffer. You don't even come close. Oh, somebody in my household is opening a bag of potato chips. Honey, stop it. Anyway, that's what you hear, which means it must be time for me to quit, guys, because my husband's bringing out the food. So give these a try and see that, yeah, no, this part B, you don't even kill the buffer. You don't kill the buffer. Oh my goodness, do you kill the water though? Check out the change. Check out the small change in pH of the buffer. Check out the ridiculous change in pH of the pure water. And you'll see that this is why we need buffers, okay? I will set up some office hours. I think the way that that's going to work is in order to make them available to everybody, I'm going to stick you guys in waiting rooms, all right? So if somebody's already in there and wanting to walk a problem with me without anybody else around, I'm going to stick you in a waiting room. And as soon as I can, I'm going to take you out of the waiting room and put you in for the office hours. But go do some work. If you really need a private conversation, email me and we'll set something up on the Zoom outside of Canvas. Because if I set it up in Canvas, everybody can see it. All right. Anything else? Go do some problems, upload stuff, and we're going to titrate like crazy on Thursday. There will be a sheet, which I hope you guys can, print, but maybe not. But you can work along. I'm going to have you guys do the math along with me on Thursday as we do all these different titration scenarios. Okay?
All right. Thank you.
All right.
Thanks,
I
Doc.
will talk to you
Thank you.
guys in a day or two, all right?
Thank you.
Just keep chugging and ask questions when you need it, okay?
By the way, does anybody want a recording of this?
Oh, have you been doing it from that side, Tommy?
Yeah.
Okay, that's cool.
If you do, just like send me a message in the chat or something, or email or whatever.
Email in the chat?
Yeah, I can post mine and then send me an email. I'll figure out a way to like get it, and it's only it's like 300 megabytes a piece. So
Yeah, they're gigantic.
yeah,
And
it's not
that's
too. I can
basically-
zip them. Maybe I can put them on YouTube. I don't know, but I'll take a look.
Yeah, we're being discouraged from putting things on YouTube on my side.
Luckily, they didn't tell me anything about that. So
Nope, you are not under those restrictions, sir. I kind of am. They're discouraging it. And yes, YouTube can take it. Zoom, not so much. Okay.
I think I have like one last thing I wanted to say. I was wondering if anyone wanted to like form a study group, like using the Discord app. I've created like a server, and I was just curious to know like how many of you would be interested in it.
Oh, I'm interested.
Yeah, that's a fantastic idea.
Yeah, I can most likely send it like online or like through the inbox on Canvas, like with a link. Once I
Yeah, that
have-
would be great.
yeah.
Yeah, you can find everyone's names there. Yeah.
Yeah, it's all there, right?
Yeah.
So yeah, I'll definitely send it through there.
Thank you. That would be nice.
All right.
Okay. We got anything else? Okay, who's doing? Oh, it's Michael. You're doing the jokes. I have the banana. I have the banana T-shirt.
Mhm.
It's full of minions. All right.
All right. Thank
I will
you.
talk to you people later. Oh, it's time to quit anyways. Okay.
Thank you, Professor.
You
Bye.
bet. You know where
Have
to
a nice
find me.
day.
Bye.
Bye.